Hello, welcome again to Completely Electrical STEM Show. This time we're going to have a look at the adiabatic process equation that electricians are going to come up against. And it all starts here. So this is the let through energy equation, if you like. And this is what we use to kind of compare our situation to what the protective device can cope with. So essentially this equation means the amount of energy the protective device will allow through, and this is the amount of energy that our cable can handle, and hopefully that is greater than that. But you know, for day-to-day electricians, that's a bit too much, really. You don't need to go into that much detail. And the adiabatic, the adiabatic equation, and I use those terms because I suppose I'm more of a physicist than electrician, and the adiabatic process is, down to thermodynamics, and the equations that we use as electricians are kind of approximate. The K factor, for example, is doing loads, taking into consideration loads of things. So, this isn't a perfect way of calculating this, but it's good enough. And you're going to see this equation in a few forms. So the first thing I'm going to do is just transpose this equation to show how it becomes those other forms. And the first one I'm going to do is the one that you see in chapter 43 of the regulations, 434.5.2 I'm going to go with, I think, and you'll see it like this. So the first thing I'm going to want to do is just isolate the t. So that means getting rid of my I squared. So to cancel it out on this side, I need to do the opposite function by itself, which is divide. And I can keep the square together at the moment because it's one term. Now, I've unbalanced the equation. I'm going to copy it this side, I squared. And then I can cancel this out. I squared divided by I squared is 1, and so we can get rid of it. And this is the first example of what you're going to see in chapter 43. And what it means is this is the time in seconds. So how long can our kind of system, our circuit, handle the fault current before it's destroyed? And again, hopefully that time is longer than our protective device will allow. So we want the protective device to trip before this time. And in this kind of scenario, if you followed the design procedure properly, that is, IZ, don't like them arrows, greater than IN, and that is greater than your design current, and your neutral is the same size as your live, then this will almost certainly comply. So this is the first example. I'm just going to transpose to the other way you're going to see it, and then we'll do an example for both, because this is really just about the equations. I could spend days talking about thermodynamics and heat dissipation in cables, but I'm just going to destroy my students' brains if I go down there. So let's just go through the equations. So this is the first one. So then let's get this back and calculate the other equation. So I'm just going to work back. I'm going to cancel out I squared this side, which means doing the opposite function by itself, and copying this time this side, and then we're back to where we were. Now in the next equation I'm going to want S isolated, but to do that I've got to kind of free it from all this madness. So what am I going to do? Well, I think the most efficient step for me to do is to get rid of these squares and then divide out K. So I'm going to do that all in one go. I'm going to square root everything that side. I've unbalanced it, so I need to copy it this side, and just note that I square rooted everything that side, so I'm going to square root everything this side. That's the rules. and then we can cancel it out. Now, a lot of my students go, well, there was 2 squares there, Craig. How do you know you can do that? Well, I mean, just play with the numbers, really. Let's try this. Let's say 8 squared times 6 squared, all square rooted. Let's just punch that in the calculator. 8 squared times 6 squared. So we've got 48. Now so if I use that to cancel them out, then we end up with just that and that. In this case, it would just be 8 times 6. So this is proving that you can cancel out 2 squares being multiplied by 1 square root. Okay, so 8 times 6 is 48. So, you know, a square root over the top of 2 squares multiplied, that works, that cancels it out. You know, we could try a different example, 3 squared times 2 squared, all square rooted. Let's see what that is. 3 squared times 2 squared, all square rooted, equals 6. And, you know, we already know, I think, well, even I know, 3 times 2 is 6. So, I mean, that's how you can practice whether a way of transposing something is actually going to work. Just put numbers in and try it. It's simple as that, really. So anyway, we're here. And all we got to do now is get rid of the k and isolate the s. So we need to do the opposite function by itself to cancel it this side, which means divide by k. And then we're going to copy it this side. And then we can get rid of x. K divided by k is 1, and 1 times s is s, so we just need the s. Ta-da. Now this equation, you're going to see it in your design, and it's normally the last thing to check. Now this is going to tell you your minimum conductor size for a particular scenario. This is still the fault current that's going to be generated by our circuit. This is the time it takes to disconnect our protective device with this fault current. And then we got this K. Now K is taking into consideration so many things. Resistivity, temperature coefficient and heat capacity of the conductor material. It's taken into consideration the initial and final temperatures of that material. It's doing a lot. Okay, so you just need to sort of go through the table in table 43.1 and look at those K values. And it is more about the material, but the other thing you need to note is the fact that a CPC, for example, let's think about a trunking being used as a CPC. Well, it's going to start at like ambient temperature, isn't it? But then during a fault, it's going to shoot up to, we don't know what temperature really, quite a lot, will depend on the fault current. But live conductors, well, they're already running hot, so then they're going to shoot up during a fault to even more. So, we need to understand them K tables. So, as I said, table 43.1, that's quite a simple table to understand, and what it tells us is that a copper conductor with thermoplastic insulation of 70 degrees, we get a value of 115. And that's, I'm going to stick to this one for now. I'm not going to make it too confusing. You're going to see this equation, not in chapter 43, but in part 5, more importantly, chapter 54. And there's another set of tables there, 54.2 to 54.6. And that describes different CPC scenarios. So if you've got a CPC within a cable, then it's similar to having it at a high temperature starting anyway, because the temperature of the live conductors are going to migrate onto the CPC. But as I say, if you had like a steel conduit being used as a CPC, that's going to start at a lower temperature, and so the K values might change. Just look through them tables, and quite seriously, if you've got any questions about it, hit me up in the comments, and I'll get back to you eventually. It might take me a while, but I will. So yeah. For our scenarios then, I'm going to stick to K. So this is 115, so this is for copper, 70-degree insulation. Right. So now we've sort of transposed these two equations and we can see how to get there. We need an example to do a scenario and see how we actually input the numbers. So my scenario, I think you can see it up there. We're going to have a circuit 50 meters long, and it's 2.5, 1.5, 6242Y or twin and earth, T and E, and it's going to be protected by a 20 amp B-type. We'll go with an RCBO to BSEN 61009, and why not make it a type AA? That seems to be the fashion with all our DC currents everywhere. It's a type A, but actually that bit's kind of irrelevant for this. Right, now, the first thing we need to establish is our ZS or ZN, because I'm going to do both equations in a minute. So we go through this version first, and I'm going to use this to check my CPC size. So if we run through what each thing is, S, which is called size of conductor, simplest form of communication there. I is the fault current that we're going to expect in RMS. T is the disconnection time of the protective device in question. So in this case, it's going to be a 20 amp type B. And K is that factor doing so much stuff. And I'm just going to put 43.1 and then 54.2 to 54.6. But for our examples, we're going to use the K value of 115. And, you know, I don't mind saying that for most of your, pen down, for most of your exams, you know, in City and Guilds in EAL level 3, we're going to stick to the 70-degree cables, copper. We're going to keep it pretty simple. I have to make noises when I get down there. I'm at that age. Anyway, so we need to solve this. First thing we need is our ZS. How do we calculate that? Well, if you watch the other videos, you'd know R1, R2 plus ZE. That's what I need. I need a ZE. So I'm going to go for 0.35 because it's a TNCS. Most common supply system, or it's going to be. Not a fan of them myself. I like TNS and I like maintenance on our networks, but let's not go there, Craig. Anywho, so to calculate this, I'm just going to quickly scribble my ZS up here. So it's going to be ZS is equal to 0.35 plus, and you'll need your table of I1 and I3 of the on-site guide, but you'll see that a 2.5, 1.5 has a milliohm per meter value of 19.51 times by our length of 50 times by our temperature factor divided by 1000. So our ZS will equal 1.52, I think. 1.52 ohms. But we want fault current. So that's not really enough, is it? That's not good enough. How do we get fault current from there? Well, we know an opposition to current. We know that this is going to be probably single phase, because I'm just telling you that now, 230 volt, 50 hertz supply, as you'd expect. So that it's just Ohm's law. You might see equations like this. So your prospective fault current, which is I, is your UO, which is line voltage to earth, which in the UK has been nominated as 230 volts. check out Appendix 2 in the regs if you want more information. So let's just keep this simple and get rid of that and just replace it with 230, that'd be easier. And divide that by your ZS, which is, impedance, or, in DC that would be resistance, wouldn't it? So voltage over the thing getting in the way of the current will give you the current. Okay, so it's just Ohm's law in disguise, nothing kind of scary here. But if we punch this in, let's see what fault current we're going to get. So 230 divided by 1.52 ohms equals 100 and... No, I'm going to have to do the calculator, I'm afraid. What's 100? Oh, could have done that. 152, Craig, that's right. 230 divided by 152, Jesus. 151. No, oh my God, what is wrong with me today? Decimals, Craig, decimals, 1.52 ohms. That's better, 151.3. Oh my God, I'm in a brain dump day. 151.3 amps. That was laboured for something so simple. There's me saying it's simple, and Anyway, so in our scenario with our ZS, if I touch the live and earth at the far point of the circuit, so if the circuit starts there and it goes to there and then returns again, at this point here, because this whole length is 1.52 ohms, it's going to generate 141.3 amps of fault current. So we can put this down here. That's what I said, then, 151. Yeah. Okay. So 151.3. Now, disconnection time. This is the bit that confuses the apprentices, because really we have to look at our time current charts in the regs, Appendix 3. But, just a little bit of knowledge of MCBs, or RCBOs even, can solve this without looking at them charts. So the way an MCB, or an RCBO in fact, works is, if enough fault current flows through that device, it's going to activate the solenoid, which will trip almost instantaneously. And when you look at the right chart, there's a little table in the corner which tells you the amount of current that solenoid needs to activate within the time stated above at the lower end. So when you look at those charts, and I've got them here, type B circuit breakers, figure 3A4, or RCBOs to the EN61009, a 20 amp needs 100 amps of current to activate its solenoid. Right. Is there an easy way of kind of working that out without looking at them charts? Well, yeah, actually. So a B-type has a multiple of times 5, 10, and D-type times 20. So what we can actually do is just look at the rating of our breaker and then multiply it by, these multiples, and that will give us the amount of current they need to activate their solenoids. So in this case, we've got 20 amp, and it's a B-type, which gives it a multiplier of times 5. So 20 times 5 is 100 amps. And when you look at that table, that's what it will state, and that's how they get there. Now, let me just draw the graph for people who haven't seen them before. So it's going to look something like this, and you got your current at the bottom, your x-axis, and then time at the side. This bit here is representing that solenoid. So once you hit that level of current, it will disconnect because it's electromagnetism, and once you reach that right amount of magnetism, it'll disconnect straight away. This bit is the bimetallic strip inside the MCB, and that takes time to kind of heat up and disconnect. And we use that for overload, and we use that bit for fault protection. And this is about fault protection. So ideally, you know, with our ZS, or in fact our Zin, you want to hit enough current so you trip it out straight away. Now, sometimes though, you might kind of come up against a circuit that already exists, and you might want to check this. So if your prospective fault current here was actually less than this value, so let's do it for our 20 amp B type, and let's say that this is 100 amps. So, you know, we're bang on the line. It's going to disconnect. What if we ended up here 90 or something? You know, I'm making it up. Well, the way you read these graphs off, you project it up until you hit the 20 amp line, and then you just go along and you read off whatever time it says there, so maybe 5 seconds or something. And that tells you how long it'll take for that bimetallic strip to warm up and disconnect. Sometimes you'll get it compliant like that, but most of the time we hope to achieve the minimum amount of current that the solenoid needs to disconnect. Incidentally, if we come this side of the line, so if our fault current is to the right of the line, then everything will be fine and it will disconnect in time. Please feel free to use my rhyme. But, you know, if it goes too far, then, you know, you might exceed the breaking capacity of that device and you might need to rethink that device. So this equation requires a few steps. You need your ZS, then you need to calculate your fault current, and then you need to go and check out these graphs and work out what your time is, and then we can input everything to the equation. But in this case, our device only needs 100 amps. We've got 151.3. So we're okay. And on this graph, it says it'll disconnect 0.1 seconds. So to use this equation now, we can plug all this in. We've got our fault current. And we can times it by 0.1 seconds and divide by 115. Now just note that this square root is only over the top half, okay, not over all of it. And let's just punch that in. So 151.3 squared times 0.1 divided by our 115, and I get 0.42 millimeters squared, because this is telling us our minimum CPC size for that fault. And what cable did we use? We used the 1.5. So we're compliant because this is the minimum size. Our size is bigger. Job done. Now, I said we'd do an example with the other formation. So I'm just going to go ahead and do that. Now with the other formation, I'm going to use it for the live and neutral loop. And so our fault current's going to be different, because with the live and earth situation that we just did, you know, our sizes aren't the same. So I'm going to get more resistance in that loop, live to earth, than I am from live to neutral, because live to neutral, we've got two 2.5s now. So this won't work either. I'm going to need a different number in here. So I'm not going to delete all of that, because all I've got to do is change that number. Now, I'm going to have to use the top of my head because I haven't got mine so good. Now, twin and earth is 1.6. Oh no, I'm going to have to calculate. 1.6 times 19. Alright, I'm going to go 14.82. Research. It's so important. I'm going to go 14.82 milliohms per meter for two 2.5s. I think that's right. Please forgive me. I haven't got time to redo this video, and I've got 23 minutes left of memory, so I better get on with it. Here's our new equation to give us our Zn, and this Zn is our live neutral loop. Now, we can use our Ze again on this, and you would for any other earthing arrangement actually, maybe not TT. But you know, in a TNCS system, actually our neutral is our earth. It's a pen conductor, a protective earthed neutral. So it's the same. So our outside bit, if you like, is the same for ZS and RZN. Anyway, this is going to change. Now we're predicting a lower value because we've got two bigger cables now. So we should get a lower resistance. So 0.35 plus 14.82 times 50 times our temperature factor still, because you know it still applies, 1000 brackets, 1.24 ohms. So we've gone down, and that means that we're going to get a higher fault current. Now, although that means that it'll disconnect quicker, it also means there's more energy going through that cable. So, you know, it's sometimes you get a bit this kind of to-ing and fro-ing, because you want a good enough fault current to activate the solenoid, but then you don't want too much because you're going to need bigger cables to cope with it in a fault. Right, so what's the fault current there? Well, 230 volts divided by our loop there. So now we're getting 185 point, I'm going to go 5 amps. So, you know, we've got 30 odd more amps going on through our circuit. Let's just remind ourselves what that other equation was that we're about to use. So this time it's time is equal to S squared K squared over I squared. That was the first one that we transposed. And we've got everything we need. These are now 2.5, this S, because that's our live conductors. And what we're going to do, we're just going to make sure that our live conductors can cope until that protective device disconnects. You know, in the real world, if you followed the design procedure, this won't really be an issue. So if your IZ is more than your IN and your IN is more than your design current, you're almost certainly going to be fine here. But let's just plug the numbers in and confirm that. So we've got 2.5 squared times our K value, which is still copper and it's still 70-degree insulation, so it's still 115. And we're going to divide that by our fault current of our live and neutral loop. This case, 185.5 squared. And you know what we want to see really is that that's going to disconnect in we want that cable to survive more than, well, 0.1 of a second. It's almost certainly going to, isn't it? 2.5 squared times 115 squared divided by 185.2 squared. So it's saying that they're going to last about 2.4 seconds, which isn't a great amount of time, and it just sort of goes to show, you know, that we kind of skirt the line quite a lot when we do value engineering. And then a little parameter here that goes off and we could actually be in trouble. But look, that complies, doesn't it? We've got 2.4 seconds, which compared to 0.1 of a second is vastly huge actually. So think of it like that, and maybe we're not putting in that tight of a safety factor. Anyway, rambling. So last things I want to say is just remind you of where to find these K factors. So we've got table 43.1, and then you've got more tables, 54.2 to 54.6, and then you got another table, 54.7. This one is simply choosing your CPC, and it will comply. And it basically It normally lends itself to giving you larger CPC cables than you might need, but it's a very easy way of selecting a CPC and knowing it will comply. I can actually go there right now and just talk you through that actually, and I might as well. So 54.7, okay, that way, Craig. No, I don't know if you're going to be able to read this off actually. God, why can't I do this? Anyway, I'll look it up yourself. It's just stupid. I need a second camera and I need a cameraman. It's really annoying having one static camera. It's driving me nuts. Anyway, so in this table it says that if the cross-sectional area of your line conductor is less than 16 mil, then your CPC will be 16 mil. If your line conductor is between 16 mil and 35 mil, then your protective conductor will be 16 mil. And if your line conductor is more than 35 mil, then your CPC will be the line conductor divided by 2. So if it was 70 mil, then it'd be 35 mil for your CPC. If it was 95 mil line conductor, it'd be half of that. So, you know, it's quite a simple way of choosing a CPC, but as I say, you'll always end up with larger cables than you need. Anyway, I think I'm going to leave it there. This was just about equations. I've tried to embed as much as I can without making it a different sort of video. I hope it's been okay. If there's any problems with it, you know, let me know. I'm planning on doing a proper design series soon, and you know, I've nearly finished it actually, but the editing has taken me ages. I was just trying to make it a bit more interesting. Anyway, look out for that, and there'll be a lot more details about, you know, thermodynamics and how the adiabatic process works. But until then, good luck, and I'll see you soon. Cheers. Don't forget them buttons. It really does boost my morale and boosts me to do more of this stuff. So if you're liking it, then thank you. I'm humbled, and yeah, thanks for watching. Cheers. Bye.